Today we're going to learn about bonding. There are 4 different types of bonding that we are going to be talking about. So the first thing that's important to know is, what is a bond? A bond is an attractive force between atoms. So it's that attractive force between atoms that allows them to stay together, okay? And something that we need to know in order to help us out with bonding is our octet rule. And it says that an atom is only satisfied when it achieves a noble gas configuration, which means it has 8 valence electrons to have that full valence shell. The exception is hydrogen and helium. So the octet rule says that an atom wants to have that noble gas configuration, that wants to have 8 valence electrons. Their exceptions are hydrogen and helium. Okay, and what's going to do is we're going to have bonds occur, different types of bonds, that allow the electrons to either be transferred or shared or to move fluidly so that you can have a full valence shell on our atoms. All right, so let's learn a little bit about the 4 types: metallic, ionic, covalent, and polar covalent bonding. All right, first up, metallic bonding. So in metallic bonding, we're going to have electrons that are moving fluidly and freely between a network of metal atoms. We call that a sea of electrons, or the kind of fancy chemistry word is delocalized. So delocalized bonding means your electrons are moving around. Delocal, local being a position. So it's not in one position, but they're moving freely around. So if you have, say, a positive charge and another atom here and another atom here, okay, these are all my nucleuses. We're going to have little electrons that are moving freely around between these. Instead of just around one atom, they're going to be moving between them. And this occurs only between metals. So metallic bonding occurs between metals, and they often end up forming a structure, so a crystal structure, to strengthen that bond, and they'll form into basically an order so that those electrons can move freely and fluidly with kind of the path of least resistance. It also means that metals are very good conductors. So they're going to conduct electricity, because if you look at all these electrons, okay, they're going to move around, and your electricity is going to be moving through these valence electrons, okay? Ductile and malleable as well. You're going to pull those electrons or hammer it down into shapes, into thin sheets, okay? You can have a lot of different things happen with metallic bonding. All right, ionic bonding. Ionic bonding is going to be an attractive force between oppositely charged atoms. So you're going to have a cation, which is a positively charged ion, right here, positively charged, and your anion, which is your negatively charged ion. So the attractive force between those opposite charges is ionic bonding, because it forms ions: your cation, your anion, your positive ion, your negative ion. And electrons are going to be transferred between atoms in ionic bonding. The electrons are being transferred. They're leaving one, and they're being gained by one. Okay, so each atom, both atoms, they either lose electrons or they gain electrons. So the electrons are literally being transferred in that ionic bond. Ionic bonding only occurs between metals and nonmetals. For example, NaCl. Na loses an electron and gives it to the Cl. So this is my little electron. Okay, and when it loses an electron, it becomes a plus charge. And when a Cl gains an electron, it becomes a 1- charge. Okay, and that is going to be how you have your little Na and your Cl combined. Okay, let me show you that in Lewis structures as well. So Na has 1 electron. Cl has 1, 2, 3, 4, 5, 6, 7 electrons. This 1 electron is going to be moved there. So your Na is going to be plus, and your Cl, if I redraw it with 8 electrons, it's going to be 1-. Okay, so it's 7, and I'm just going to put it in a little bracket so I know that that's what I'm talking about. Okay, so that's your ionic bonding. It occurs between metals and non. So we're going to do some practice with ionic compounds. I'm going to do the first 3, and then I want you to try the next 3 in your notes. Okay, so for this, if I have a 3+ charge over here, and I have a 3- charge on the phosphorus, I'm going to completely balance out. So my ion formula is going to be FeP. Okay, I only need one iron and one phosphorus to create a molecule. However, let's try my next one, so number 2. Okay, number 2, I've got a 3 plus charge over here, so 1, 2, 3, and I've got a 1 minus charge over here. So I need one of these and 3 of these. Okay, so I need 3 chlorines, and the way that I'm going to write that is I'm going to write FeCl3. Remember, your subscript stands for the number. Okay, so this is 1 and 1, this is 1 and 3. Okay, let's try magnesium, Mg. Mg's got a 2 plus charge, so I can represent that each one with a little 2 plus. And then each chlorine is going to have a 1 minus. So I need 2 atoms of chlorine to balance out my 2 plus charge. So I have 2 plus, 2 minus. So that'll be MgCl2 because I've got 2 chlorines. So actually, let's do 4 together. So we're going to do 4 together, and then I'm going to have you do 5 and 6 on your own. All right, so Mg, I've got 2 plus and 1 atom. And a phosphorus, I've got 3 minus, 1, 2, 3, and 1 atom. Okay, I've got a 2 plus and a 3 minus, so that's not going to be enough. But you can see that the common denominator is going to be 6. So if I put 2 of my phosphoruses, I have a total 6 minus charge, 1, 2, 3, 4, 5, 6. And then I can balance that over here by adding 2 more Mgs. Whoop. And I'll have 6 pluses as well. So that means I have Mg, and there are 1, 2, 3 atoms, and then I have P, and I have 1, 2 atoms. Okay, so that's going to be how I do that. I would like you to try 5 and 6 on your own. That's going to be your homework. Okay, so try those. The next type of bonding is called covalent bonding. Covalent bonding is when you have electrons that are shared between atoms. Okay, the electrons are shared. They're not transferred, but they're actually shared, kind of like a tug of war. Okay, and it occurs between nonmetals. It occurs between nonmetals. So carbon and oxygen are both nonmetals, so that's going to be a covalent bond. And water, hydrogen and oxygen are all nonmetals. Remember on your periodic table, this is my loose sketch, everything to the right is nonmetals as well as hydrogen. Okay, so those are your non-metals. Make sure you know that. Polar covalent bonding. Covalent bonding is kind of the large subset, and then you want to look for the subset, okay, of polar covalent bonding. So that's what the difference is. The difference is that in a polar covalent bonding, you've got unequal sharing of electrons. Okay, you've got 2 medium-sized guys who tug a war. Then your covalent bonding, it's going to balance out. If you've got 1 big guy and 1 little guy, they're not going to pull the same. They're not going to share that rope the same. Okay, the big guy's going to share kind of more of it. Same thing happens with your electrons. When they're sharing, okay, when they're sharing electrons, it's not going to be equal sharing. Remember, all atoms have different abilities to attract electrons. That's what electronegativity is. So they have different abilities to attract those electrons. So you have something with a strong electronegativity versus something with a weak electronegativity. The electrons are going to be shifted over more towards one area. Okay? So polarity, we say, is the difference in ability to attract electrons, or the change in electronegativity. All right? So when we do that, we're going to talk about dipoles. So I'm going to draw my trend for electronegativity. It increases going up and over. It's electronegativity. Okay, so if I have, for example, something like fluorine, and bonded to it is a sodium atom, or no, let's do carbon, a CF bond. Okay, this is a carbon and a fluorine. My carbon is going to be less electronegative. My fluorine is going to be more electronegative. So I draw this little partial charge. The sigma minus goes on the more electronegative. Okay. On the other one, I draw a sigma plus. That's less electronegative. Okay, and this just shows us where the electrons are going. They're going to go towards the F. Okay, so this is called the dipole arrow. And the dipole arrow shows us where the electrons are going. Where do the electrons go? Okay, so you have to remember your electronegativity trying to help you do this. Your partial charges, you're either going to be a partial positive or a partial negative. It's kind of like an 8 without the last bit of it, or like a S with a tail. Okay, that's going to be your partial charges. All right, so that's it. So make sure you know your bonding, and we'll be able to work on that tomorrow. Okay, thanks.